sometime a function that you may want to differentiate may have the form of a function of another function of a variable. For example, the sine of x squared is the sine function applied to the squaring function of x. In those cases, all you need to do is apply a simple formula called the chain rule. The chain rule is given in terms of functions f of x, u of x, and their composition f of u of x. Or to use some arbitrary names, we could name the inner function picking, the outer function enjoyment, and the variable is noses. Then the chain rule says that the derivative of the enjoyment of picking of noses is the derivative of enjoyment of picking with respect to picking evaluated at picking of nose sub 0 times the derivative of picking of noses with respect to noses evaluated at nose sub 0. If you've already heard that a million times, don't worry. We are really going to try and dig deep in this video, get to the root of the issue so that you understand not just why the chain rule works the way it does, but why it works the way it does. Look at sine of x, and we're going to let it gradually transition into the sine of x squared by raising the exponent on the x from a 1 into a 2. So it goes from sine of x into sine of x squared, and we can see exactly what is happening here. Only one thing. The points on the function move from the right side of the screen over to the left side of the screen. And that's it. And so it's not impossible to find the derivative based on the derivative of the sine function. You look now and see that sine of 4 has slid over to 2, and sine of 9 has slid over to 3 because sine of 3 squared is 9. This means that the whole part of the sine curve that used to stretch from 4 to 9 over 5 units has been scrunched into the space between 2 and 3 of just 1 unit. But the sine of 4, 5, 6, 7, and 8 are all in there. Sine still goes up and down just as much as it used to. Only now, instead of doing that over 5 units, it does it over 1 unit. And since the derivative is basically the upping and downing divided by the distance, this means that the derivative of the sine of x squared is 5 times higher on average in that interval than the derivative of the sine of x was between 4 and 9. So now let's say we want the derivative at some particular point. How do you figure out how much scrunching there is right around a particular point? Well, for one thing, you can notice that there's more scrunching further to the right on the x-axis. X squared gets more scrunched up than it is on the left of the x-axis. Out at x equals 5, x squared is 25, and it goes all the way to 26 in 1/10 of a unit of x. And at x equals 4, x squared goes from 16 to 17 in 1/8 of a unit of x. So it's more scrunched up at x equals 5, a little less scrunched up at 4, it's even less scrunched up at 2, and the scrunching is not uniform over the large scale, but if you zoom up around a point, the scrunching is pretty uniform around that point, close enough that we can actually take a derivative. So the question is, how do you know exactly how scrunched it is? How did we know that at 5 it was only going to be about 1/10 of a unit to get from 25 to 26? The answer is that we know how fast x squared changes with respect to x. If it's changing 10 times faster at 5, which it is, then it stands to reason that you would get from 25 to 26 in only 1/10 of a unit of x. So the scrunching is the derivative of x squared. And for any compound function, the amount by which the outer function is scrunched when it takes the inner function as its argument instead of just the variable is the derivative of the inner function with respect to the variable. Because enjoyment takes picking as its argument. If picking is changing really fast with respect to noses, then enjoyment is also changing really fast with respect to noses. But if picking is changing really slowly with respect to noses, then enjoyment of picking is more flattened. On any compound function that takes x squared as its inner function, at x equals to 3, that compound function is going to be scrunched up by a factor of 6 because x squared is changing 6 times faster than x at x equals 3. So now we're basically done. Say you want the derivative of the sine of x squared at x equals 2. You say, okay, I know the derivative of sine. It's cosine. And at x equals 2, the sine of x squared is 4 times more scrunched than the sine of x. So the answer is 4 times the cosine of 2. And you would be so close, you know? And it sounds like it makes sense, but that's not true. It's not true. The reason is that at over 2, we have the part of the sine curve that was sine of 4. And it slid over from sine of 4, and its slope is still proportional to the slope of sine of 4. And so the right answer really is 4 times the cosine of 4. That's it. Thanks for watching.